Okay, so let's try and look at some aspects of the solar system in a bit more detail. We'll look at primarily a few sort of disjointed aspects of it, which I thought might interest you all. One is the temperature of the planets. What do temperatures of the planets depend on? Then we'll look at how did the moon form, what are the possibilities? And we'll briefly look at the origin of the solar system and discuss a little bit about extrasolar planets very, very briefly. Okay. Now, what do you think the temperature of the planets would depend on? Any one of you can unmute and suggest?
Proximity to the sun and what their atmospheres, if any, consist of.
Yeah, proximity, and then what did you say, Ahan?
And the composition of their atmospheres.
Composition of the atmospheres. Okay, very good.
And also the reflectivity or the absorptivity of the rock that they're composed of.
Reflectivity, absorptivity. Yeah, okay. All right. Now, not just the rocks, but of everything, actually, I will just look at that. All right. So it will depend on distance from the sun, as Ahan just mentioned. It will depend on the atmosphere. It will also depend, in cases where there's an internal generation of heat. Okay? There could be internal generation of heat which gets propagated. The amount of light that is reflected back from the surface. And that is denoted by what is called the albedo. Albedo is reflected light upon incident light. Very often when they use the word albedo, they're referring to the visible region of the electromagnetic spectrum. But they also give what is called as the bond albedo, where they consider the entire electromagnetic spectrum. But more often when they refer to albedo, they're talking about the visible region. So when you see that A is equal to 1 for a perfectly reflective body, that means all the light is just being reflected off, nothing is going to heat the planet at all. And A is equal to 0 for a completely black planet, means everything is absorbed. A varies from very dark, for example, for the moon is 0.11 to very bright for 0.67 for cloud-covered Venus, because these clouds are often quite reflective, good reflectors, as we just mentioned when we talked about the Earth as well, that the clouds reflect more light than the water or the rocks. And the giant planets, the albedo is roughly about 0.5. And as we mentioned earlier, that Earth's albedo is variable due to cloud cover, but average is in the ballpark of 0.3 something or so. And the visual geometric albedo for Mercury and Mars are 0.106 and 0.15. Not a hell lot different from the moon. These are all sort of rocky planets as well. Now let's just do a little sum and we'll look at that. Okay, consider a planet. Temperature is governed by radiation received from the sun. We know the solar luminosity. Flux is luminosity of the sun divided by 4 pi distance of the planet squared. And the energy absorbed by the planet will depend upon pi rp squared, where r is the radius of the planet, and that is the surface which it is facing the sun, surface area. Now, energy absorbed by the planet will depend upon the albedo, right? Albedo. So 1 minus a fraction is absorbed. Okay. So that is the energy absorbed by rp squared L sun, 1 minus a 4 pi d squared. So as we just mentioned, albedo is a fraction of radiation which is reflected. And I mentioned briefly about bond albedo as well. So these are the typical numbers, we just mentioned. 0.09, moon is similar. Venus is large. Earth is in the 0.3. It will keep varying depending upon which source you look, but it's usually in 0.3 and a bit above it. Neptune is similar, Uranus is similar, Jupiter is 0.5. Okay. Now, but one thing is receiving the radiation, but it's also is radiating energy away, right? Because it's at a certain temperature. So if we say that solar energy received by the planet is by rp squared f, where rp is the radius of the planet. So you can calculate luminosity, you can calculate for the sun, okay? Then energy radiated by the planet is what you have to take into account as well. that will also radiate like a black body. So it is 4 pi rp squared sigma T effective temperature of the planet to the power of 4. And if it's in equilibrium, then the energy received and the energy radiated would have to be equal. And if you try and equate these two, then what you will get is the effective temperature of the planet is equal to 279 into 1 minus a to the power of a quarter, 1 AU upon dP to the power of half. So in this equation, you can see that the radius of the planet does not come into the picture. And if you plug in the numbers of albedo about 0.3 or so at a distance of 1 AU, this is a temperature about only 250 K. So this is much smaller than what is the what is the measured temperature on the Earth, right? And that is because of the atmosphere. As Ahan mentioned, that it has a greenhouse effect where the atmosphere retains the heat, and that is what increases the temperature. So this is the basic physical processes which governs the temperature of the planets. Because part of it is in the heavier planets, a little bit could be internal generation of heat, but a major role is played by how far away you're from the sun and the atmosphere which you have, which can trap the heat.
How does Jupiter generate internal heat?
The conversion of gravitational potential energy as in the interiors of planets is what will give rise to generation of heat over here, because there are no nuclear reactions going on over there. It is just gravitational potential energy that gives rise to heat energy or kinetic energy of the particles. Temperature decreases with distance that you can see over here from Mercury, and Venus gets very high because of the atmosphere. But otherwise, you can see that except excluding Venus, which has a very high temperature, that it generally follows the trend of having a lower temperature as you go further and further away from the sun. When we look at stars, we will see that what is the minimum mass which is required to generate nuclear reactions. For example, if Jupiter was a lot more massive than what it is right now, then nuclear reactions would have been possible and would have generated energy by nuclear reactions. But when nuclear reactions are not possible, it's gravitational potential energy, which sort of makes a difference. Okay. Now, so temperature for planet, mean surface temperature for terrestrial planets, and the mean cloud temperatures of the giant planets. So this is what we have just seen as well. Again, you can see over here that the Earth to Venus distance is only about 1.38, and because it depends on the square root of the distance, temperature should have been different by only a factor of 1.2. But you can see that there is a huge difference, and that is, as we have just said, and as Ahan also pointed out, about the atmosphere playing an important role in the temperatures of the planets. So this is just a picture of the atmosphere of the Earth and the crescent moon as seen by the International Space Station. But one thing which one wants to highlight over here is the delicate balance in which we are in on the Earth. Because we know today that the Earth consists largely of nitrogen, and the carbon dioxide is in very small quantities, and oxygen makes up a significant component. But for example, if the temperature increases significantly, there is carbon dioxide which is dissolved in the oceans. There's a huge amount of carbon dioxide. There's also carbon dioxide locked in the rocks. So if these get released with increases in temperature, you could have a runaway greenhouse effect and have a completely uninhabitable atmosphere. Sadly, today's bulk of the political leadership don't appear to realize the consequences of global warming with very short-time goals of economic profit. But the tragedy is that if there's a runaway greenhouse effect, I'm not sure that there's anybody who would be able to control that. So it's important that we look after our planet in our own little way, whatever we can do, consume less energy, have as less of a carbon footprint as possible. Okay. Now, just a brief discussion on the atmospheres of planets. Okay. Now, we talked about the atmosphere affecting the temperatures of planets, but what is it, do you think affects the fact that the moon doesn't have an atmosphere, Mercury hardly has an atmosphere, Earth has an atmosphere, Venus has a rich atmosphere. What do you think determines the existence of atmospheres and planets.
One should be gravity.
Very good. Gravity is one aspect of it.
Yeah, and then the heat of the sun, I guess.
Sorry?
The sun's effect on it, like the heat of the sun from the sun.
Heat of the sun. Okay.
Yeah, but I guess that's not a great one because Venus still has an atmosphere.
No, but that's also an important contributor. We'll have a look at that. Okay.
Magnetic field.
Magnetic field, not very much actually, not very much, because magnetic field would affect the charged particles. Okay. And a lot of the atmosphere would not be charged. Ionosphere is charged, but a lot of it would be neutral as well. Okay. The solar system must have also formed and evolved from a protoplanetary disk. We'll look at that in a short while. And composition across the protoplanetary disk should have been reasonably similar. All right. So ideally, we should have had similar atmospheres, but we don't. In the inner planets, we have high density, we have rocky material, little contribution to the total mass from the atmosphere. And you can see over here, I've just given you one example, that the total mean mass of the atmosphere is about 10 to the power of a few times 10 to the power of 18 kilograms. This varies due to water vapor content and all that. So yeah, there's, but you can see when you compare to the Earth's mass, it's 6 orders of magnitude lower than that. Okay. So you can see that the atmosphere has a very little contribution. And initially the Earth should have also contained a lot of hydrogen and helium and traces of heavy elements, because that is what the universe is made of. And that is what Jupiter is made of. That is what the sun is made of. So across the disk of the protoplanetary disk, which in short are referred to as proplyds, the abundance should have been similar. But today we know that that is not the case with the atmospheres of the planets. So proximity to the sun is one effect which heated the gas to beyond their escape velocities, leaving rocky material. Then also releases of gases due to volcanic activity. And these could have been further modified by life. Initially, to start with, microbial life, which we know flourished on the Earth. So let's, atmosphere of Venus as seen by ultraviolet, observations from Pioneer Venus Orbiter 1979. Venus is believed to have lots of water in the early stages, but the sun's luminosity increased, water vapor vaporized, was a runaway greenhouse effect, and it has settled down to this present equilibrium state where it is hot due to the solar radiation, which is trapped inside with the gaseous environment of carbon dioxide, water vapor, etc. Okay. Now, let me just ask you a question, okay, at this stage, that we know that, for example, when we want to measure the rotation of a planet, we look at one feature and we can see it moving and we record it. Now, when a planet like Venus is enveloped in gas and dust, okay, how do we infer the rotation of the planet? And I mentioned earlier that it has a very long rotation period, right? And it is also peculiar in the sense that unlike all the other planets, this has a retrograde motion. That means the spin is in the opposite direction to its orbital motion. So how do you think we will we infer the rotation of Venus? Okay. What people have done is that they have bounced radar signals off the surface. Okay. What happens in radar signals that burns off the surface? That if it is bouncing off a surface which is moving, then it is going to be Doppler shifted. So they send it off at a well-determined frequency, determine the frequency at which they receive the bounce radiation, and from that they can infer the rotation of Venus. And today we can see, I've shown you a picture of the atmosphere of Venus. But Venus is rocky inside, right? And how do we know that? Anyone?
We know because we can estimate its mass and thus its density.
Actually, we have landed on Venus, the Venera landings on Venus. We have landed on Venus, explored the surface of Venus. It consists of basaltic rock. There's evidence of lava outflows, volcanic activity, and a lot of impact craters on Venus as well. But one interesting thing about the impact craters on Venus is that when we looked at meteorites hitting the Earth, we talked about the large craters, we talked about the small craters. The craters on Venus are all very large craters. And that is because only the large would have survived going through this atmosphere and hit the rock surface. Okay, hit the rock surface. And the smaller would have actually, just disintegrated while going through this thick, dense atmosphere of Venus. But I don't think we have so far put seismometers on Venus, so we don't have really recorded seismic waves to study from seismic waves the interior of Venus. But we have learned a lot from the Venera landings on the surface of Venus. Now, just a summary of the constituents of the atmospheres of Venus, Mars, and Earth. Carbon dioxide, you can see, dominates Venus and Mars. Nitrogen is small quantities, whereas in the Earth, nitrogen dominates. Trace amounts of argon, water vapor, small quantities. Oxygen, you can see, is large over here for the Earth, whereas in the case of Venus and Mars, it is very small. And I put the surface pressures as well. So what you can see is that the evolution from carbon dioxide to an oxygen-rich environment in the Earth has not only been caused by geological processes or volcanic eruptions, which may have changed the atmosphere, but also due to the development of microbial life, which use the carbon dioxide to photosynthesize and give up oxygen. So that is one of the prime reasons how the atmosphere on the Earth has changed as well. And if you look at Mercury, there's hardly an atmosphere. There's exospheres of Mercury and the Earth's moon, very, very tenuous cloud of hydrogen, helium, envelops both Mercury and the moon. Density is extremely low. You can see the density at sea level on Earth is about 10 to the power of 25 molecules per meter cubed, whereas on the surface, on the exospheres or surface of Mercury and moon, it's 14 orders of magnitude lower. And even the pressures are extremely low. Collisions are rare among these species. And so there is hardly any atmosphere over there at all. Then you can ask yourself what happened to the atmosphere. And as you have correctly pointed out, that gravity has a role to play over there. Okay? Gravity has a role to play because you need gravity to hold on to the atmosphere, right? And that will depend upon also the temperature. The gases making up the atmosphere must be there at the time of formation or may be released subsequently, as for example, by volcanic action, as we just mentioned. The temperature must be warm enough that the gases do not freeze and settle on the surface, okay? And the gravitational object must be strong enough for the body to retain the gas given the object's mass and temperature and composition of the atmosphere. So these are the conditions for an atmosphere to exist. So if they don't have an atmosphere, then clearly these conditions are not being satisfied. And let's just have a brief look at that. So you can calculate the escape velocity due to gravity, right? Escape velocity is given by 2gm upon r to the power of half, where m is the mass of the object, and r is the distance from it. So if you take r as the radius of the planetary body, it depends on m and r, the radius of the body holding it. Okay. Now we need to compare this with the average thermal velocity of the particles in the atmosphere. And I've just put the kinetic energy is equal to 3/2 kT, 3 degrees of freedom, half kT per degree of freedom. And the number of particles in a given velocity range is given by the Maxwell-Boltzmann distribution for a gas in thermodynamic equilibrium. And I've given over there the most probable velocity, which is 2 kT by m raised to the power of half. Okay. Now one can equate these two and try and get the temperature at which the gas would escape. Escape velocity we have written, and a thermal velocity we have written, and we can equate these two and calculate and see what the temperature would be for it to escape. M is the mass of the object, capital M, and small m is the mass of the molecule that we are considering, all right? Escape velocity, just to remind you, this is something you'll be quite familiar with. You can see for Mercury is 4, Venus about 10, Earth is 11, Mars is 5, Moon is 2. Jupiter, Saturn, Uranus, Neptune, they're all much larger. So a combination of low gravity and temperature is what leads to the loss of an environment, of the atmosphere. So the outer Jovian worlds, they hold on. Now here, what is given is the location of the different bodies over here, planets as well as moons. And this is the surface temperature. This is the escape velocity. And for different species, hydrogen, helium, water, oxygen, you can see at what temperature that would be, what would be the escape velocity. Right? Now you can see that everything is below, for example, Jupiter, Saturn, Uranus, and Neptune. So nothing is escaping from it. It would have more of the primeval gas which formed the solar system. Just like hydrogen and helium are the main constituents of the star. When you come to the Earth and Triton, you'll see that we lose hydrogen and helium. We retain water, and we also retain water in its liquid form, as we just said. But when you come to Moon and Mercury, you can see that combination of velocity and surface temperature. You lose almost everything.
It just in the graph you're showing of surface time versus escape velocity, Earth is above the line.
Earth is above the line, so water is being retained, right? What is below it will be retained. What is above it is what will disappear. So Earth has lost hydrogen and helium.
Oh, okay. I misinterpreted the graph. Okay.
So hydrogen and helium it is lost. Whereas Jupiter's, everything below where it is located will be retained. For the Mercury and Moon, you can see everything is above it. So Mercury and Moon has lost almost everything, right? Except for a very tiny exosphere. So just gives the percentage composition of the Sun and the outer planets, planet Jupiter, Saturn, Uranus, and Neptune. And although there are variations because in the surface of these planets, but you can see that they've considered hydrogen molecule over here, hydrogen and hydrogen molecule, because in the planets it would be existing in molecular form. And as we saw earlier, that under intense pressure it will also occur in liquid form, and it will also be metallic with a lot of free electrons. Whereas in the Sun it will be entirely ionized plasma. Okay, but you can see that these are all pretty high values, right? And so is helium, right? And there are small quantities of methane, ammonia, etc. And in the outer planets, these will all be in, methane would be extremely cold and icy. Now, how do you think the Moon formed? What do you think happened to it? How did the Moon form? Any of your...
a large asteroid impacted the Earth in the early stages of its formation, and a chunk of mass that got ejected from the Earth as part of the collision got trapped in an orbit around the Earth.
Excellent, Ahan. But what is the evidence for it? And what is the evidence against other possible scenarios?
I believe the compositions were similar, and I can't recall it right now. I actually did this in geology 2 semesters ago.
Okay, excellent. Okay, that's true. Okay, let's see how did the Moon form. I'll just tell you some of the theories which have been discounted. One is the fission theory. The Moon was once part of the Earth, but somehow separated from early in the history. One is the sister theory, that thing that the Moon formed together, but independent of the Earth, And that may be true of many of the moons of the outer planets. And they formed in the vicinity and fell under the gravitational influence of the planet. And the capture theory, the moon formed elsewhere, and just as asteroids keep traveling, and Ceres, Vesta, they were in the asteroid belt, some were formed elsewhere in the solar system, and it was captured by the Earth. But these theories have actually been discounted for various reasons. The fission theory, the moon was once part of the Earth, but somehow separated from it early in the history. This was suggested in the late 19th century without much of observational evidence. And more recent people have done calculations and shown that this is very unlikely and not possible, not likely. And also, as Han mentioned, there are similarities in chemical compositions. Also, there are some distinct differences, but we need to understand why the differences are there and why the similarities are there as well. And that is where, if it is exactly the same material we separated out, then everything should be the same. But there are differences. The sister theory, the moon formed together, but independent of the Earth, as we believe many moons of the outer planets formed. Now, this is not popular, unlikely given the similarities and differences of chemical compositions, because if it was the same material which formed together over there, then it's not easy to get the viable explanation for this. And the capture theory has also been discounted because it's very difficult for such a large body to be captured from elsewhere and to have an orbit which is also nearly circular rather than eccentric, and also abundances of some of the major isotopes. Rule this out. So then we come to what Ahan has studied and shared with us, called a giant impact hypothesis. Impact by a large body, large object about 1/10 the mass, leaving the Earth unshattered. Because if it was much more massive, it would have shattered the Earth itself. And detailed computer simulations have been made to suggest that several percent of the Earth's mass could be ejected by such a body. Stony mantles from the Earth's impacting body, and not from the metal core. And the ejected vapor will form a ring which cool and coalesce to form the moon. So you can, if you look up the web, you'll find references to very detailed simulations from it. And this also explains why the absence of metals found in the core is understood. The volatile materials have been lost, and it also explains the similarity of isotopes. So both computer simulations and the similarity of abundances of isotopes of oxygen is what have led people to believe that this is the way the moon has originated. But this is not the way for all moons. Some moons may have formed in the vicinity of for example, the Jovian planets, and may have been gravitationally tied to the parent planet as well. Now, just a very brief discussion on planetary formation. We'll probably discuss this a little bit more when we come to discussing star formation. But we have discussed this and alluded to it at various points of time, that these stars form in giant molecular clouds when they collapse. And due to the angular momentum in the collapsing component of the cloud, it will form a disk. And along the disk, depending upon the perturbations and the gravity, various parts will condense to form planetesimals, which will probably coalesce to form planets. So this is what is sort of what has been simulated by theoretical calculations. And today we find evidences of these disks kind of structures, protoplanetary disks, in many stars. I've just shown you some examples of images with the Hubble Space Telescope, with the Atacama Large Millimeter Array, because these rings would also radiate in the millimeter and infrared wavelengths. And you can see a whole, sort of different categories of them. You can see them breaking it up into ring kind of structures over here, with perhaps planetesimals which will coalesce to form planets. So the details, effects of magnetic fields, All these things are still, areas of research, but at least the broad picture of a collapsing cloud with angular momentum forming a disk, the disk forming the planets and the rings and the various components of the planetary systems, is something which holds up to scrutiny from observations as well as theoretical work. As I just mentioned, that when the disk forms, the angular momentum, the rotational energy would increase as 1 upon r as 1 upon r squared, as material goes closer and closer to the central object, the central star over here in this case. So you need a redistribution of the angular momentum. So some of the angular momentum is carried outwards, some of it goes inwards, allowing the star to collapse. And then this angular momentum, which also carries outwards, forms this kind of structures, which you talked about. And materials lose angular momentum due to viscous forces in the disk. And how a star also loses angular momentum is something which is, quite interesting to investigate. And these are still areas of research. And the role of magnetic fields, what do they play when these stars and the disks form? So these are interesting astrophysical questions. But we also know from observations that the disks don't last very long. So the planets would have formed very early on in the formation of a planetary system. So a disk of dense gas and dust around newly formed stars, which are called protoplanetary disk or proplyds. So I've shown you images of a lot of these proplyds, which have been imaged at different wavelengths, whether it be infrared, millimeter wave, or the optical wavelengths. Some have also been imaged at radio wavelengths. This is the thermal emission from them. And disks have radii up to about 1,000 astronomical units or so. Okay, so you can see that these are, given the sizes also, that they are very well sizes of the planetary systems that we see today. And temperatures are roughly about 1,000 in the inner region, but it's going to cool. But we see that the disks rapidly disappear. We know, for example, that our solar system, as you all have also correctly mentioned, is about 4.5 billion years. But when you try to estimate the ages of these disks, okay, or look at the fraction of disks in stellar systems of different ages, by the time the stars come to about 10 or 15 million years old, there is really hardly any disks seen at all. So disks are only seen in young stars. So the inference is that the disks don't last very long. So the disks probably rapidly, condense to form, planets, dwarf planets, asteroids, you name it, whatever the small system bodies that have been identified for our solar system. But the disks don't last very long. But this is a route to the formation of a planetary system with a central stellar object. So the planetary systems that we see, that the Earth of age of the meteorites, would be almost similar to that of the age of the solar system. Okay. Now, just to introduce you to one or two small things. One is the existence of life elsewhere. Today we have no evidence.
What is the disk fraction in the last slide? If you go back.
Okay, 1 second. Let me just go back one slide.
What does the disk fraction stand for?
This fraction is, suppose I had, let me just take one example over here. Suppose I had stars whose ages I estimate to be, say, 2 million years. Okay. Now, of all the stars of 2 million years, what fraction have a disk? Okay.
Oh, okay. So it's showing how the disk coagulates into the star over time.
Over time, that's right. So you can see that when you see young stars, most of them, almost all of them, have over 80% of them have detected disks over there. But when you go to older stars, 15 million years old, you hardly find any with disks at all. So the scenario is that the disks form in all stars, but as the star ages, the disk, it condenses to form planetary systems, and you don't see it as a disk anymore. So the formation of a disk is the route to form planetesimals and planetary systems very early on in the formation of the star itself. Okay? When the gas cloud collapses to form the star, it has a disk around it, and the disk also condenses to form planetary systems around it as the star, protostar, collapses to become a star. Okay?
Okay.
Now, this is the Drake equation. Now, we are always worried about whether there is life elsewhere. And that is one of the most challenging questions. The search for extraterrestrial intelligence or extraterrestrial life has been an ongoing question, and a lot of effort has been put into it. We have no sign of life anywhere else still today. And but this is the famous equation, which was called the Drake equation. And this just calculates the probability of existence of life elsewhere, considering the number of civilizations in the Milky Way whose electromagnetic emissions are detectable, the rate of formation of stars, the fraction of stars with planetary systems, the number of planets per solar system environment suitable for life, the fraction of suitable planets on which life actually appears, the fraction of life-bearing planets on which intelligent life emerges. For example, you may have life, but you may not have intelligent life. I mean, even in our Earth, right, the earlier microbial life originated billions of years ago, but there was nothing what we can describe by the term intelligence over there. Then FC, the fraction of civilizations that developed a technology that produces detectable signs of their existence. And L is the average length of time such civilizations produce such signs. Okay, so this is what is known as a Drake equation to estimate the probability that life would exist. And when you actually, because the sheer huge number of stars that exist, not only in our galaxy, but in other systems as well, that if you put all these factors together, it is almost impossible not to believe that there must be life elsewhere. And they're in the SETI Institute, which is the search for extraterrestrial intelligence, they're nearly, working on nearly of these, lots of research questions related to these various aspects, which lead to the possible existence of life elsewhere. And today we know that there are, over 4,000 extrasolar planets which have been detected. And Didier Queloz and Michel Mayor got the Nobel Prize for detection of the extrasolar planet, similar to, a solar type extrasolar planet, although extrasolar planets were discovered orbiting a pulsar earlier. And there are over 4,000 of these now. And there are, very clever techniques of detecting them, very fine instrumentation as well, because you need to measure tiny changes in Doppler shifts if a planet is orbiting about a star. And when you're looking at Doppler shifts, it's more easy to find Jupiter-sized planets close by, because that will induce a larger velocity of motion in its companion star. Whereas if you want to look at, then when it eclipses the star, you try to measure a very small change in brightness, in intensity, which you want to measure brightness. And so these are very small changes, but the technology and the instrumentation has been developed to measure these small changes, not only from the Earth, where it was first done, but space missions, which have revolutionized the field. Extrasolar planets is a completely interesting area in its own right. But the point here is that there are dozens which are also in the conditions which should be habitable. And this is a site which looks at or lists potentially habitable planets, although there are no evidences of life so far. So we cannot be a freak accident in nature, and we have only, touched the tip of the iceberg in terms of extrasolar planets and those where life can potentially exist. But there are a lot of interesting questions about the origin of life itself. For example, life consists of RNA, DNA, which are made up of amino acids which go on to make them. And amino acids are organic compounds that contain amines, which are compounds of NH2 and carboxyl COOH with the functional side chains denoted by R over here. And amino acids exist in both left and right-handed forms. It's your left and right-hand gloves don't fit into each other. They're sort of mirror symmetric. And this comes from the Greek word chirality. And there are about 500 or so naturally occurring amino acids are known, but only about 20 of these form the basis of all life on Earth. And all these amino acids are left-handed. And this has been one of the very profound discoveries. I've given a link to a very popular sort of article in the Smithsonian magazine, where some of you who are doing biology can read much more deeply into it. And the question is, did homochirality originate in the depths of space or on Earth? And you can study this in meteorites, for example, where you find evidence of organic material, and also from samples which you pick up from asteroids, for example. So sometimes in the meteorites, you see excess of left-handed ones in studies of meteorites. But we also find a reasonable number of right-handed ones. But when there is a significant excess, there is left-handed. It is left-handed as far as I'm aware. So chemistry of life seems to be intimately related to cosmic biochemistry. And this is something which will keep opening up as more and more missions are there to pick up samples from outer, near-Earth asteroids. This is where NASA's OSIRIS-REx has picked up a sample from the near-Earth asteroid Bennu, which is named after an ancient Egyptian mythological bird associated with the sun, associated with creation and rebirth. So this happened in 2020, and Bennu is about 321 million kilometers away from Earth. It is on its way back, and it will reach here in 2023. So this will give us a view of the pristine solar system. And these are aspects which may also give us some clues as to how life may have originated. We can't, return things from very far away, maybe sometime in the distant future, but at least the near-Earth asteroids and comets are being explored by spacecrafts. There was some argument about life in Venus from the detection of phosphine. The result was not confirmed by relooking at it, and the original authors have also now withdrawn the results. So there's no evidence of life anywhere else except on the Earth, but there is no reason as to why life cannot exist elsewhere, as we know life may have evolved, or as we know our physics and biology and chemistry. So today's lectures was to give you a brief overview of the solar system